We're talking today about intermolecular associations. So the first thing distinction I want to make is between intramolecular associations, which are going to be the things holding a molecule together, the bonds that we have been discussing, covalent bonds, polar covalent bonds, or ionic interactions. And ionic interactions are going to be special. We'll talk about them in a minute. That's different from intermolecular associations, which are the things that hold molecules together as a liquid or a solid, and the things that are overcome as you convert it to a gas. So as you boil something, you're breaking intermolecular interactions. You're not breaking the intramolecular interactions. When you boil water, you don't break the hydrogens away from the oxygens, but you do break adjacent water molecules away. And the same is true if you boil some other liquid. We want to look at what those intermolecular associations are. And one caveat that I've mentioned is next year, as you're looking at biological molecules, they are so large where a protein folds over itself, a protein that has a molar mass of 70,000, relatively mid-sized protein, is going to fold over, and what will be holding the protein in those detailed structures will be these weak intermolecular associations, even though technically they are intramolecular in that case, because they're holding different parts of the same molecule together. We're going to call them intermolecular anyway. Intermolecular associations are always electrostatic, and they will depend upon, the strength of it will depend upon whether we have a permanent dipole. So in other words, we have one side of the molecule that is positive and the other side that is negative, or we have temporary dipoles. Temp dipoles can be induced, caused by something nearby, or somewhat random. These will generally be the weakest. Permanent dipoles will generally be stronger. And for example, when we looked at the plot of boiling point versus mass, all of the hydrocarbons from methane, ethane, propane, pentane, all the way up, they fell on a pretty good line. And all of those were being held by sort of random distribution changes in the electron distribution. So random changes in electron distribution, we'll have a name for that in a little bit. On the other hand, ammonia and water had very high boiling points because those were permanent dipoles. Those are polar molecules. And we will be looking at how these forces interact. So let's start with ionic compounds, which are not molecules at all. So really, we're not talking about intermolecular interactions, and it's straightforward. So ionic interactions are very straightforward. We've addressed these with Coulomb's law. And we've measured lattice energy. And these, again, are not molecules. These are just positives and negatives that are held together, arranged in a way that allows you to pack them closely. And so in that case, you have a full charge difference, at least one electron's worth of difference between the two entities, the cation and the anion. And if a compound is ionic, you can determine that by having the difference in electronegativity if it's greater than, say, 1.7 to 2, somewhere in that range, something becomes ionic, and you have just an ionic interaction. And once you've determined that the molecule is ionic, that the compound is ionic, you don't have to think about other possible interactions. Ionic compounds are held together by ionic bonds, and you're done. So you're done in terms of assigning what types of interactions are holding that thing together. If it's ionic, well, that's what's holding it together in a crystal. The next thing to think about is dipole-dipole interaction. So an interaction between two dipoles. And the example being given here is hydrogen chloride. I know you think of it as hydrochloric acid when it's dissolved in water, but it's actually a compound that is considered a covalent compound. Now, the two things you need to know if something is going to be polar is, are there polar covalent bonds? So if you look up the electronegativity difference, you find that chlorine is a lot more electronegative than hydrogen. So it's not going to be sharing the bonded electrons equally. You're going to get electrons pulled over towards the chlorine. In both cases, part of the molecule will be partially negative. The other part will be partially positive. That's a lowercase delta. So we use delta to mean difference in. So this is a little difference in. So it's not a capital delta. It's not a full electrons charge, but it's partially negative and partially positive. Okay? So if something is partially negative and partially positive, you're going to have one side stick to the other via the dipole-dipole interactions. So in the flow chart, is it ionic? Find out that it's ionic, then you're done. If it's not ionic, if it's a molecule, a covalent compound, then you have to ask, well, are the bonds polar? And then if the bonds are not polar, then it can't have a permanent dipole. So if it's non-polar bonds, obviously not a polar molecule. If there are polar bonds, but the shape doesn't allow for any asymmetry, then it's also not polar. So let's look at some examples. You've looked at these before, some of these before. So NH3, we have small polar bonds, all drawing more or less in the same direction. That has a dipole. We have strong polar bonds in CO2. However, they cancel out. So it's non-polar. And in general, if it's a new molecule you haven't seen before, you're going to have to draw a Lewis structure and figure out if it's polar. So you have, let's take some examples. This is one you've seen before, formaldehyde. The electrons are being drawn slightly to the carbon from the hydrogen, more strongly to the oxygen from the carbon. This is about 120 degrees. So this is a polar molecule. Another one that we've looked at is this guy. And remember, whether or not I put the H's and the Cl's next to each other doesn't matter, because all of these are around 109. And this is also a polar molecule, an overall dipole that way. So dipoles will interact by virtue of one side being positive and the other side being negative. An important variant on the dipole-dipole is something called the ion dipole. This is the interaction between a salt, an ionic compound, when it dissolves, say, in water. So you've seen diagrams like this before. This is where you have a permanent dipole in the case of water, right? Negative side, and then you have a positive ion like sodium plus. Similarly, if there were chloride minus, which would be larger over here, it would be interacting with the positive sides of water. So when you're talking about interactions among two different types of things, one thing to consider is ion dipole. The next sort of subset of this is what's called an induced dipole. So ionic things tend to dissolve in water. Polar things tend to dissolve in water. What about nonpolar things dissolving in water? Well, they generally don't dissolve that well, but they do dissolve. For example, you can get carbon dioxide to dissolve in water. Under pressure, you can get a lot of it to dissolve in water. That's how you make fizzy carbonated sodas. You can also get oxygen to dissolve in water, which is a very good thing if you're a fish, because you need that. But it doesn't dissolve all that well. How does a nonpolar thing dissolve in water? Well, it dissolves in water via what are called induced dipoles. So you have a nonpolar molecule, I actually wrote it, and it's right there written. I didn't need to write it out. So you have a nonpolar molecule, oxygen, right? You know it's nonpolar because certainly, well, it's a nonpolar molecule because, and the straightforward answer is oxygen is nonpolar. I could also take something like carbon tetrachloride. Well, it has polar bonds, but the vectors will all cancel out. All of the vectors are drawing out to the outside. These outside surfaces are all slightly negative, so this is not a polar molecule. Yes, it has a slightly negative surface, but it's nonpolar. O2 also has a negative surface because it's got a lot of electrons, but it's nonpolar. However, when it comes in contact with water, you can induce a temporary dipole. So the fact that one side of the molecule is slightly negative will push electrons, so the slightly negative side of the water will push the electrons over to one side of an oxygen molecule and temporarily induce it to be polar. So that's known as an induced dipole, generally fairly weak interactions. The next force has to do with random fluctuations in the cloud of electrons. Yes, I know it's not really a cloud, but it's sometimes useful to think about it. And these are known as London dispersion forces. And all you need for London dispersion forces is a surface with electrons around it. In other words, any molecule. So all molecules. Not ionic compounds, but all molecules can have these, or have these. Because every molecule has a surface and it has electrons on that surface. And what can happen is just because of random fluctuations, one side of the molecule ends up with more of the electrons over here, leaving this side slightly positive, which then draws electrons from this guy and makes it slightly positive. So you can think of the electrons sloshing back and forth. And the two things that are going to determine the strength of this interaction is how many electrons on the surface. And then how big is the surface area? The more surface area you have for interactions, the more interactions you're going to see. And so, for example, if we compare, what is this? 1, 2, 3, 4, 5, 6. This is hexane, C6H14. And it's got a pretty large surface area. It's stretched out. It's a long kind of linear, it's actually kind of zigzaggy if you draw it out properly. But it's a long linear molecule. And we plotted, I don't know if I think we got as high as hexane. We may have skipped it. I know we did octane. We plotted that on your chart of boiling points, and it was one of the higher ones. It was liquid at room temperature, boiled off at higher temperatures. It doesn't have a particularly large number of electrons on the surface, but it has a fairly large surface area. And as a result, it gets fairly strong London dispersion forces. So London dispersion forces one-on-one are fairly weak, but as you get to a very large molecule, you can have fairly strong interactions by adding up the interactions over a large surface. So let's compare a couple of possibilities. You also looked at these three things on your chart: N-pentane, isopentane, and neopentane. All have same mass, all have same number of electrons, same number of electrons on the surface. Not a particularly large number, but it's the same number of electrons available to slosh around. And pentane has highest boiling point, and this has the lowest. Now, they're all pretty close together, but they did show different differences in their boiling points. And so the question is, why? And the answer is surface area. So we looked at two reasons. It's how many electrons and how much surface area. They both have the same number of electrons, but a linear form like this has greater surface area and this has least. This is almost spherical, and a sphere is going to get you less surface area than a linear. And this intermediate one, isopentane, has an intermediate amount of surface area. Next question. Carbon tetrachloride and methane, this has a boiling point that's quite low. This one has a boiling point of minus 171, 161 I think it was. And this one has a boiling point of positive 76 degrees Celsius. And the question is why? Well, they have a fairly similar surface area, however, more electrons. And the reason for this is that chlorine has a great many more valence electrons than hydrogen. And so more electrons that can be polarized and therefore slosh from one side to the other. So, overall flow chart. One, is it ionic? And for that, you just look at difference in electronegativity. Greater than 1.7 to 2. If so, ionic compound, and you don't have to worry about it anymore. You're done. You know it's an ionic compound. That's what's holding the thing together. It's not a molecule, so you can't really talk about intermolecular interactions. 2, if it's a molecule, LD forces will be in play. Because all molecules will have a surface with electrons, and all molecules can have random fluctuations. Is it polar? If not, then only LD. If yes, then it will have dipole. It will have dipole-dipole interactions. Very straightforward. Is it ionic? If it is, you're done. If it's not ionic, you're definitely going to say that there's London dispersion forces. If it's a polar molecule, you ask if it's polar, you're going to have to look at the shape and the polarity of the bonds. And if it's polar, then you're going to have dipole-dipole. You can have a few special cases, such as ion dipoles for mixtures. And you can have induced dipoles. Those were sort of special cases there. So if it has polarity, if it's a polar molecule, chances are the polarity is going to be a big contributor to its boiling point and the intermolecular associations. If it's LD only, then more electrons on the surface, more surface area. Both of those lead to stronger bonds, stronger LD. Last thing I want to talk about is the special form of the polar bond. The hydrogen bond is a special dipole. For a hydrogen bond to occur, you need hydrogen bonded to something very electronegative. And only three things are electronegative enough to cause this. Hydrogen bonded to an oxygen, hydrogen bonded to a nitrogen, or hydrogen bonded to a fluorine. And this is a special case of a dipole because in the case of hydrogen, there are no other electrons. Any other polar bond, there are going to be valence electrons that are pulled over, but there'll also be internal shell electrons, non-valence electrons, that will be still kind of guarding the nucleus or covering the nucleus of the atom. In hydrogen's case, because the electrons are being pulled over here, this basically ends up being an exposed proton. This has a very, very positive surface, and it's a narrowly defined positive surface, a really specific place where it's almost a full positive charge, just not quite. Because the electrons are being pulled all the way over towards fluorine with very little electron density back over here to cover up the hydrogen nucleus. So this would be what's called the hydrogen bond donor. On the recipient side, the acceptor has to be either oxygen, nitrogen, or fluorine, and they can interact. So you can have oxygen interacting here with the hydrogen, or you can have nitrogen interacting with one that's being drawn away by the oxygen. So it doesn't matter. It's not that an OH donor can only interact with an O on another surface, but and nitrogen could interact with it. Really good case of this would be water. So I now have, with the next water molecule, this hydrogen bond. Ammonia, another thing that generates hydrogen bonds similar to water. And I could have the nitrogen of ammonia interacting with the hydrogen of oxygen. Hydrogen fluoride is another one. Now, hydrogen fluoride can never be found in the middle of another compound, so it's never going to be important in biology. Hydrogen fluoride, fluorine can only make one bond, so there's no other compounds that have a fluorine-hydrogen bond, whereas there are lots of other compounds that have oxygen hydrogen bonds or nitrogen hydrogen bonds. For example, methanol, right? And this side will have only London dispersion forces, but this side can make a hydrogen bond. Because you'd have to have a fairly tight fit here. It's a little bonds. Fairly tight fit here because you'd have to have, say, the hydrogen from the next methanol interacting like this. And you could have that hydrogen bond there. So hydrogen bonds require hydrogen bonded to one of these three very electronegative atoms, and then a similarly very highly electronegative atom to be the acceptor. Now, hydrogen bonds are the strongest of the non-covalent interactions. They're the strongest of the intermolecular interactions. They're what's holding water together as a liquid at relatively high temperatures. They're what's holding your DNA, your A's bonded to T's together. They're what's holding proteins together in large measure. So we're going to be looking at these a little bit more detail as we go on. So again, on the flow chart, first, is it ionic? If it's ionic, you're done. If it's not ionic, then some London dispersion forces will occur, so you're going to check that box right away. So if it's a molecule, LD is a component, It may not be an important component, however, especially if the molecule has a strong polarity. When you get to larger molecules, then LD forces can actually be very strong. So this now explains what you saw in the plot of boiling point versus molar mass with the other functions that we talked about. If you're interested about LD, once you've discovered that LD is the most important thing holding molecules together, well, they're going to be stronger if there are more electrons on the surface, such as with carbon tetrachloride, compared to methane, right? More electrons, or they're going to be in a more spherical or more linear shape. The more linear the shape, the more surface area you're going to have, and that was isopentane, neopentane, and N-pentane, N-pentane being the most surface area, and therefore the slightly higher boiling point. And I think I'll stop there.